I'd like to welcome you to the World Year of Physics, which is an international celebration of this science. And as you may know, recently in the SAT tests for college entrance, they took a section out which was word comparisons or word associations, and they decided to put in essays, which of course all young cell phone users really love to do. But what I'd like to do is I'm going to give you some words, and I want you to associate the one word that explains everything that's going on with these words. Flight of a bumblebee, rainbows, champagne bubbles, snowflakes, car crashes, tornadoes, butter. Skiing, ice cream, the smell of a skunk. Diamonds, photosynthesis, music, sailboats, the performances in Cirque du Soleil. What is the one word they all have in common? Physics! You can say it! Physics! Isaac Asimov has said physics is the basic science of all sciences. Everything else is just a specialized aspect of physics. In the recent book by Bill Bryson, A Short History of Nearly Everything, which I was a little disappointed because there was no mention of Paris Hilton in it, he said, at the end of the 19th century, as it drew to a close, a young German named Max Planck was trying to decide what he was going to devote his life to, mathematics or physics. And all of his friends talked him out of physics because, as they said, all the great discoveries have been made. Scientists had pinned down all of the major systems of electricity, optics, magnetism, kinetics, gases, acoustics. They had discovered the X-ray, the cathode ray, the electron, the radio wave. They had invented the ohm, the watt, the Kelvin, which would forever confuse people who were trying to cook in Fahrenheit. They had invented the joule, the amp, which of course led to rock and roll, and the little erg, which looked nothing like a hobbit. Yes, all that was left in physics was a little bit of cleanup around the edges, and the world of physics was finished. Until 1905, a landmark event took place. It was really the dawn of the age of science. 3 small papers were published in a small little journal by a young Swiss bureaucrat who worked in a patent office who had no university affiliation, no laboratory, no library. He was a technical examiner, 3rd class, who had just recently applied for a promotion to be technical examiner, 2nd class, and he'd been turned down. He'd been rejected, but today he may be one of the most famous scientists of all. When we think of his bushy white hair, his bushy mustache, his wrinkled clothes, how can we not remember the name Lester Delgado? Thanks for laughing. No, he was a man of simplicity, Albert Einstein. A reporter asked him one time, why do you use the same soap to wash your face and to shave with? And he said, why 2 soaps? That would be too complicated. And yet, he was a very complicated person. He's one of the few scientists in the world today that we still make jokes about or with. A stitch in time would have confused Einstein. And of course, Gary Larson, in one of his most famous cartoons, Great Moments in Science, Einstein discovers that time actually is money. But I'm curious, how much do you really know about Al? I'm going to give you 4 questions, and at the end of the evening tonight, I will answer them. But here are the questions, something for you to ponder. Known for his snowy white hair, what was the original color of Al's hair? When he was born, doctors were very concerned about a physical abnormality. What was it? In 1955, Al had something removed. What was it and where is it today? And at what point in his life did his deep religious training come in conflict with his studies of science? Something for you to think about. And to ponder even more, I'd like to introduce Roy Gould, Dr. Roy Gould from the Harvard-Smithsonian Center for Astrophysics. He's a colleague, I can say a friend. We've, of course, partied together, made bail together when we needed to get out. He's out of the Science Education Department at Harvard-Smithsonian. He's the director of the NASA Smithsonian Education Forum on the Structure and Evolution of the Universe. He's also been an associate producer for NOVA. He was the principal investigator for Cosmic Questions, an interactive display that opened here in the museum and has traveled the world and thrilled millions that have seen it.
Good evening, everyone. Can you hear me okay? All right, good. Excuse me, my name is Robin Simons, and I'm the director of the Charles Hayden Planetarium here at the museum, and I'd like to welcome you to the Museum of Science for our billionth Lowell Lecture Astronomy Series. You know I'm exaggerating, but I'm actually not sure how many years we've done this, but it's been for decades. And we're very pleased to see so many of you here this evening. This is one of the venerable lecture series that are run by the Museum of Science with several partners, which I'll talk about in a moment. I don't want to forget anything here. We have several partners, and I said that. One of our primary partners for this lecture series for decades, as I said, as many of you know, is the Harvard-Smithsonian Center for Astrophysics, which, as I'm sure most of you know, is one of the primary research institutions in the world. The people in the front row don't agree with this, but one of the primary research institutions in the world in astrophysics and cosmology. Is that funny? Oh. Now it looks like I'm saying nothing. Okay. All right. I'll explain the captioning in just a minute. Did I say that? That's Kathy. We'll talk about Kathy in a minute. That's Kathy up there. So our first partner, our main partner is the Harvard-Smithsonian Center for Astrophysics, one of our main partners. The other primary partner we have is the Lowell Institute, which has funded this series for many years. The Lowell Institute of Boston, of the great Lowell, Massachusetts family, and they very generously support this series and support your free admission to this series. Yes, they are wonderful. Thanks to them. Another partner is WGBH, our local public television station, which most of you probably know. WGBH partners with us on this series in order to put all of these lectures on the Internet. And this lecture in its entirety will be on the Internet within 2 or 3 weeks. It takes a little bit of time to get it on there, but they're up in the back tonight, up in the back of the room, filming the entire lecture. So if you want to see this lecture again, or if you have friends who missed it, who would like to see it within a couple of weeks, it will be on the Internet. And the thing to do is to go to WGBH's website, which is wgbh.org, and click on the forum. Is that right, Melissa? Click on the forum, and you can. There will be a number of things there, but you can find this lecture on there within a couple of weeks, in streaming video and on demand. And our last but not least, our other partner, as you have noticed, is a company called Caption First of Illinois. Caption First is a new partner of ours. This is the first night we're trying this, and we're having, as you can see, as you've already noticed, this entire lecture captioned for the deaf and hard of hearing. And the way this works, it's neat. You're the first audience that's getting it, so I'll tell you how it works. Kathy is in Indiana. There she is. And Kathy is typing away like a maniac out there. She's hearing everything I say, and she's typing away, and then it gets sent back through the internet, captioned here. So it's a wonderful new system. It may not be a new system, but we've just found out about it, and we're trying it tonight for the first time. If it works well, the museum will be using systems like this in the future, I hope. So that's a very exciting addition to our evening tonight. So that's enough introductions, except I have to introduce, last but not least, David Aguilar, whom many of you know. David is, what are you, David? David is the moderator of our series. I knew that part. I'm looking for his title. David is the Director of Public Affairs for the Center for Astrophysics, and he has been doing this since 2000. We love working with him, and as many of you know, he is the most entertaining guy in Boston. And so please welcome David.
I'd like to welcome all of you here tonight to the first day of spring. No, it's not true like the Red Sox. I'm just messing with your minds right now. I'd like to welcome you to the World Year of Physics, which is an international celebration of this science. And as you may know, recently in the SAT tests for college entrance, they took a section out which was word comparisons or word associations, and they decided to put in essays, which of course all young cell phone users really love to do. But what I'd like to do is I'm going to give you some words, and I want you to associate the one word that explains everything that's going on with these words. Flight of a bumblebee. Rainbows, champagne bubbles, snowflakes, car crashes, tornadoes, butter. Skiing, ice cream, the smell of a skunk. Diamonds, photosynthesis, music, sailboats, the performances in Cirque du Soleil. What is the one word they all have in common? Physics. You can say it. Physics. Isaac Asimov has said physics is the basic science of all sciences. Everything else is just a specialized aspect of physics. In the recent book by Bill Bryson, A Short History of Nearly Everything, which I was a little disappointed because there was no mention of Paris Hilton in it, he said, at the end of the 19th century, as it drew to a close, a young German named Max Planck was trying to decide what he was going to devote his life to, mathematics or physics. And all of his friends talked him out of physics because, as they said, all the great discoveries have been made. Scientists had pinned down all of the major systems of electricity, optics, magnetism, kinetics, gases, acoustics. They had discovered the X-ray, the cathode ray, the electron, the radio wave. They had invented the ohm, the watt, the Kelvin, which would forever confuse people who were trying to cook in Fahrenheit. They had invented the joule, the amp, which of course led to rock and roll, and the little erg, which looked nothing like a hobbit. Yes, all that was left in physics was a little bit of cleanup around the edges, and the world of physics was finished. Until 1905, a landmark event took place. It was really the dawn of the age of science. 3 small papers were published in a small little journal by a young Swiss bureaucrat who worked in a patent office, who had no university affiliation, no laboratory, no library. He was a technical examiner, third class, who had just recently applied for a promotion to be technical examiner, second class, and he'd been turned down. He'd been rejected, but today he may be one of the most famous scientists of all. When we think of his bushy white hair, his bushy mustache, his wrinkled clothes, how can we not remember the name Lester Delgado? Thanks for laughing. No, he was a man of simplicity, Albert Einstein. A reporter asked him one time, why do you use the same soap to wash your face and to shave with? And he said, why two soaps? That would be too complicated. And yet, he was a very complicated person. He's one of the few scientists in the world today that we still make jokes about or with. A stitch in time would have confused Einstein. And of course, Gary Larson, in one of his most famous cartoons, Great Moments in Science, Einstein discovers that time actually is money. But I'm curious, how much do you really know about Al? I'm going to give you 4 questions, and at the end of the evening tonight I will answer them. But here are the questions, something for you to ponder. Known for his snowy white hair, what was the original color of Al's hair? When he was born, doctors were very concerned about a physical abnormality. What was it? In 1955, Al had something removed. What was it, and where is it today? And at what point in his life did his deep religious training come in conflict with his studies of science? Something for you to think about. And to ponder even more, I'd like to introduce Roy Gould, Dr. Roy Gould from the Harvard-Smithsonian Center for Astrophysics. He's a colleague, I can say a friend. We've, of course, partied together, made bail together when we needed to get out. He's out of the Science Education Department at Harvard-Smithsonian. He's the director of the NASA Smithsonian Education Forum on the Structure and Evolution of the Universe. He's also been an associate producer for NOVA. He was the principal investigator for Cosmic Questions, an interactive display that opened here in the museum and has traveled the world and thrilled millions that have seen it. He's also designed exhibits not only for here, but also for Los Alamos and other facilities. He is also the principal investigator for pre-college curriculum from the ground up. Tonight, he's going to speak on Who Needs Physics? Dr. Roy Gould.
Thanks very much, David. Now I finally understand what I'm supposed to be talking about tonight. And I want to thank all of you for being here this evening, and I especially want to thank the museum. It's a double treat to be here because I worked here for many years, and it's one of the great cultural institutions in the country. I realized to my horror a few moments ago that absolutely nothing that I say tonight will have any practical value whatsoever. And so perhaps we can just answer the question, who needs physics? Do we all need physics? Can we all just agree with? Good. Okay, now we can move on. It's, of course, it's true that physics is wonderful for solving practical problems, but physics is also about wonder. And what I'd like to do tonight, since we're celebrating the World Year of Physics, and really celebrating, if you like, the end of a century of modern physics, introduced in 1905 by Einstein's remarkable breakthroughs, I thought it would be fun to just step back and take a look at what are some of the wonderful ideas that physics has given us over the last century. So this talk is not going to, I'm sorry that it's not going to focus on a single idea and then go on in depth the way physicists usually do. Instead, what I want to do is really just a kind of an impressionistic view of a number of big ideas, and I've chosen these actually just rather personally. I'm sure you could come up with a much longer list. So 5 big lessons from physics tonight. Number one is that no idea is too crazy to be true in nature. And we'll see what that means. Number two, there's more to the world than we see with our senses. We've also learned that the world is connected in unusual and mysterious ways, and maybe we'll try a little demonstration if we have time to see one example of that. Number four, we are somehow fundamental to the universe. And I'm going to stop and just say to Kathy, I know that I'm supposed to speak slowly and distinctly, but I wasn't planning on doing that tonight. So hang in there, Kathy. We are somehow fundamental to the universe, by which I mean that the universe that we see and describe in some way depends on the fact that we're here. A very controversial topic, but I want to just mention it and touch on it tonight. And finally, the idea that even infinite complexity can arise from very simple rules, and we'll take a look at a nice pattern that illustrates that very nicely. Okay, then, let's just dive in. I want to start with a question. Take a look at this photograph and tell me, is this a photograph of a real house or a doll house? How many think it's a real house? Ooh, not very many. How many think it's a doll house? Huh. Why is that? Anybody have a... Well, let me put it this way. How many of you are absolutely certain that this is a dollhouse and not the inside of a house waiting to be sold? Well, we see some certainty here. Well, the fact is, well, I'm not going to say. The fact is we can't really tell from this photograph without comparing it with the real thing. So let me ask you a more difficult question about the real thing. What scale is the universe at? Who set the scale of the universe? Does the universe have a single scale, or can the scale of the universe change from place to place or moment to moment? Well, I can't really see past these lights, so I can't see all of it, but I'll just fill in for you. Common sense says that the universe is all built at the same scale. A foot here in Connors Theater ought to be the same as a foot outside, a foot in Paris, a foot on the moon. That's certainly what Isaac Newton thought hundreds of years ago. It seemed obvious to him, although his rival was not so sure of that, Leibniz. And it turns out, now we're going to go back to 1905 to our first crazy idea, it turns out that the scale of the universe is not fixed, and I want to explain a little bit what that means. I don't want to make these ideas plausible. I just want to show you the progression of the ideas and really focus on this one crazy idea that the scale in the universe is not fixed, and see what other crazy ideas it led to. So 1905, Einstein discovered and published in his 1905 paper the discovery. He didn't put it in these words, but with hindsight, your scale depends on how fast you're actually moving. The faster you run, the more you actually shrink in the direction of motion. And you may not have noticed this, of course, because the effect is very, very small. If you had noticed it, it wouldn't be a crazy idea, and we wouldn't be talking about it tonight. And I don't want to say more about this, except to say that that opened the door to a whole host of other remarkable ideas, all of which flowed from this single idea that the scale of the universe is not fixed. For example, in 10 years, Einstein had discovered that your scale also depends on where you are. For example, as you move closer to a massive object like the Earth, your scale actually shrinks a little, so that we are actually more of a dollhouse model here in Connors Theater than we would be up in the roof or up on the top of Mount Everest. Again, this effect is incredibly slight, part per billion, say, on the surface of the Earth, so we don't notice it. On the other hand, we have learned over the past century that this effect has an enormous, is seen to the extreme at the surface of a black hole. In fact, it was way back in 1942 that J. Robert Oppenheimer and his colleagues realized that when certain kinds of stars near the end of their lives, they can actually collapse under their own weight, and they distort the scale of space and time around them so much that, in fact, the scale becomes zero at the very entrance to a black hole. So if you could move right to the edge of a black hole, you would become the ultimate dollhouse figure, going to zero scale. You might wonder, what happens if you fall into a black hole if you're already at zero scale? I mean, can you shrink even further? Can you go to negative scale? And it turns out, I see some people shaking their heads, it turns out, yes, you can. And I just say this as an aside to those of you who like this sort of thing, that when you fall into a black hole, something very strange happens. Time and space trade places. And in fact, we've learned in the last 100 years that negative scale actually corresponds to time. And so along the direction that leads you into the center of the black hole, you're following what becomes the forward direction in time. And that, by the way, is why you can't ever get out of a black hole. It's sort of a misconception that it's about gravity. It's actually, of course, this comes from Einstein's theory of gravity. But the idea is that you're carried into the center of the black hole by the forward motion of time. And you can't get out of the black hole for the same reason, unfortunately, that we can't go back in time. All right, let's just move along. Okay. In another 10 years, Einstein and his colleagues, here you see George Lemaitre, who is the Belgian mathematician and priest who is said to be the father of the Big Bang. And with Einstein, he discovered that your scale also depends on when you are. By which I mean the scale of the universe actually gets smaller as time passes. The scale of the whole universe gets smaller as time passes. Who would have imagined that? Again, I'm not going to lead you through the logic, but it all follows from Einstein's initial 1905 paper and the other known laws of physics. Let me just describe a little bit what this means and how to picture it. Here you see a picture of a big chunk of space up here, and I've put a ruler across it. And so this chunk might be enough to contain many, many galaxies. And as time passes, the scale of the universe actually shrinks, by which we mean that these rulers, these distance markers, actually get smaller. And so we can fit more of them across that chunk of space, and we say that, we actually say that the universe has expanded. Most of you are used to seeing it this way, this alternative way. But this shows a chunk of space, and it shows the space expanding or stretching. A lot of us have heard of that. The universe is expanding and space is stretching. That's also a misconception. The universe is not expanding outwards. What's actually happening is that the scale is decreasing. So you never have to picture what the universe is expanding into and how space can push all of that existing space out of the way. But that doesn't matter. That doesn't matter. The main point here is that new space is continuously being created. And this is one of the astounding conclusions that flow from Einstein's 1905 breakthrough. And it means that the creation of the universe was not a single event, but in fact is an ongoing process. And that although our own matter was indeed created in the Big Bang about 14 billion years ago, the space in the universe, most of the real estate of the universe, was in fact created within the last 2 billion years. And you have in every cell of your body genes that are older than 2 billion. Did I say 2,000? Yes, you have genes that are older than 2 billion years that are, in fact, have remained unchanged for over 2 billion years. So in fact, some of us, part of you, is older than most of the space in the universe today. It's an astounding realization that the universe is in a process of becoming. Anyway, I want to drop this idea now, but the take-home message then is that a single crazy idea that the scale of distance is not fixed in the universe has led to all these marvelous and wonderful discoveries, black holes, the expansion of the universe, and so forth. I want to move on to our second idea, that there's more to the universe than we see with our naked eye. In particular, there are colors of light beyond the rainbow. You all know that, I'm sure. and I just wanted to show you a couple of images that seem to me really powerful images from the last century. And I'll just remind you that all the colors that we see, of course, are colors in the rainbow or mixtures of those colors. But there are colors or wavelengths of light beyond the rainbow that we can't see. For example, out beyond the red is infrared light, and there's also microwave and radio waves, which are also a form of light. And way out beyond violet, you know, there's ultraviolet light, and then X-rays and gamma rays and so forth. And though we can't see these other forms of light, there are animals, for example, who can. Here's, does anyone know what this is? It's, did somebody say a flower? Yes, yes. What kind of flower? It's an evening primrose, just on the garden stand this week. And this is what it looks like to us. It's very pretty, but in fact, it's much prettier if you're a bee, because bees see ultraviolet light, and they have a relationship with the flower, and so the flower has developed pigments that absorb and reflect ultraviolet light, and has actually created patterns that only the bees can see. So this is what you see if you're a bee. You see those patterns in the center are sort of called nectar guides. They guide the bee into the sweet part of the flower. So here's what we see. Here's what the bee sees. There's more to the universe than what we see. And of course, we've learned that in the cosmos as well. And I just want to show you two other quick pictures. Who would have guessed, for example, that at the center of galaxies like this beautiful galaxy Centaurus A, which unfortunately you can only see from the southern hemisphere, who would have guessed that there lurk gigantic black holes, a billion times more massive than our own sun? And of course, you can't see that with an ordinary telescope picture, but when we use instruments that allow us to see beyond the visible, in this case an X-ray, this is the Chandra X-ray telescope. Whoops. Yes, we see a flower. we see this incredibly dynamic object in the center. This is what you're looking at there is, first of all, the bright spot in the center of the galaxy is the black hole, and it's sending out a huge jet, really a gigantic death ray that's 100,000 light years or 1,000,000 trillion miles long, one of the largest structures in the universe. And nobody had any idea that there were such things out there until we were able to look at the universe with instruments that took us beyond the rainbow. Here's just one other view. This is a Hubble picture. This is the furthest that we can see in the entire universe. This is the Hubble ultra-deep field, which they've managed to animate for us, but it's actually the actual pictures of the galaxies. And who would have imagined that in between the galaxies, there's light that we can't see? In fact, the entire universe is filled with light left over from the Big Bang itself. A common misconception you might have is that the Big Bang happened at a single point. A lot of people are very confused by that. No, the Big Bang actually took place everywhere in space and simultaneously, and its light, in fact, fills the entire universe, and so traveling in all directions. And so light from the Big Bang that's left over is, in fact, continually reaching Earth, and we've just recently been able to image it. Many of you have probably seen this. This is from one of the NASA missions, the WMAP mission, and there have been other ground-based telescopes as well that have imaged this. Light left over from the Big Bang. So if you could see this light, and it's in a wavelength we can't see, but if you could see it, then at night the entire night sky would be bright. In fact, the light would overwhelm all of the stars, so you'd never see the stars. And it seems quite amazing. In fact, I find it almost mysterious in a way that nature has arranged for us to be able to see all the way out to the edge of our observable universe and to start to see our origins in the Big Bang, because the universe could have been cloudy and our view might have been not as beautiful as it is. All right, and I might just add this, what don't we see in our own lives? You know, is your spouse saying something to you that you're not hearing? and are there instruments that could help us hear what they're saying? But I want to just quickly move on now to our next idea, which is that nature is connected in unusual ways. And unfortunately, I can't do justice to this in a few minutes. But I did want to show you an unusual feature. It's a phenomenon that I find very beautiful, and it does connect up with the art world as well. So I'm going to do a little experiment first. I have this cereal box here. Take a good look at it, and I'm going to just ask you, to, in a moment, to close your eyes for just 5 seconds, and I want you to tell me if I've turned the box and moved the box at all. Okay? So, okay, close your eyes. Okay, you can open them now. Now, have I moved this box at all? No? Some of you say no, some say yes. If I turned it exactly once around, 360 degrees around, would you be able to tell? Would it look exactly the same? Would it be exactly the same? Why not? I might have shaken it, but suppose I could now, let's idealize this, turn it exactly once around. It would be very hard for you to tell. One of the discoveries, and I think it's really amazing in the last century, is that you actually have to, that when you turn an object around once, it doesn't come back to itself. You have to turn an object twice around in the same direction for it to come back to itself. And let me just explain what I mean by that. And this is something that comes to us from the branch of mathematics called topology, which deals with connections. If you could actually connect strings from this cereal box, let's say to the walls, and now I turn it around once, of course the strings would all be twisted, and there'd be no way to untwist them without cutting them. If I turned the box twice around, the strings would get even more twisted, and yet incredibly, it would now be possible to untangle the strings. And unfortunately, I can't do that experiment with you tonight, although I'm going to do something hopefully close to that, and you can try this at home. Now, who cares? Does this have anything to do with the universe at all? It turns out it does. There is an object in the universe that exhibits this effect, and that's the lowly electron, of which we're all made, of course. So if you turn an electron around just once, and you can do that, by the way, using tiny magnets. It's actually possible. It actually changes its properties. You have to turn it twice around for it to come back to exactly the state it was in. And without going into it, it turns out that that phenomenon is necessary for electrons to be able to build up the atoms that we're made of. And so if that were not true, we wouldn't be here tonight. There would be no matter. So it turns out to be very profound. It turns out also to be a phenomenon that's used in the Balinese wine dance. And I'm just wondering if we have a volunteer tonight who might actually try the Balinese wine dance. I'll just talk you through it. Do we have...
You're looking at me, aren't you?
I'm looking at Steve. Could you do it now? I have a priceless wine glass with me that I thought... Oh, no. Maybe we'd better just imagine the wine glass, okay? So the idea of this is that, Christine, is that you're going to hold the glass, this imaginary glass, in your hand, as they're doing here. And the idea is, in the dance, is that you're going to turn your hand 360 degrees like this, and you can see that your arm is now twisted. And you would think that you couldn't keep going, but in fact, in the same direction. But in fact, you can, and I'm just wondering if you can try that. You can do it. You can do it. If you keep going, and you can do it if you. That's it. You have to get. The idea is to keep your hand stationary. That's it. That's it. That's beautiful. That's beautiful. That's wonderful. That's wonderful. Does everybody see that? Goes around once, and then keep doing. Okay, you got it again. Needless to say, it takes practice before you can join the... actually, this is a Persian troupe, I'm told. But, all right, let's move on. I want to move on to a topic that's again, I can't do justice to in a few minutes, but it's so important I couldn't leave it out. And that is what is becoming a crisis in current physics and cosmology. And I want to just touch on it now. It's the realization that we are in some way fundamental to the universe, by which I mean that when we describe the physical universe and ask why is it the way it is, the spotlight turns around and focuses on the fact that we're here in some way. And it's related to this question, why is our universe so remarkably hospitable to life? Let me just explain what I mean here. The mission of physics has long been to find out why the universe is constructed the way it is, and not some other way. So, for example, there are lots of givens in nature. For example, why is gravity not stronger than it is or weaker than it is? Why does an electron not weigh more than it does or less? Why isn't light faster or slower than it actually is? And you can play this game with lots and lots of givens, these fundamental constants or parameters of nature. And one thing that's been discovered is that if you try to imagine a different kind of universe and you vary these, so you make gravity a little stronger, or you make light a little faster, or make electrons a little lighter or heavier, sometimes even by just 1%, one way or the other, it turns out that the universe doesn't work. You wind up with a universe in which life cannot exist, either because atoms aren't stable, or you can't form planetary orbits, or stars burn up too quickly, and so you can't evolve life. And I'm just going to give one quick example of one of my favorite instances of this. This is a particle that physicists know is. Let me just stop this for a second and say. When I was a physics student and we learned about neutrinos, I remember the comment of one famous physicist who said, "Who ordered that? A neutrino is a cousin of an electron, but it has no electric charge. And this is a particle that is so boring that billions of them are passing through us at this very moment and not getting your attention at all." Okay? And they spend their entire lives, in fact, the whole lifetime of the universe, more or less doing nothing, except, now we go to astronomy, except for that 1 second of glory in their lives when at the center of a star that's about to explode, they actually trigger the explosion and actually create the explosion of the star. And I'm just going to let this run. So this is actually an animation of a star that's about to collapse. Its core is collapsing, and then it's going to explode. And if this didn't happen, then all the elements formed inside a star would not be scattered out into space, and we wouldn't ultimately be able to form planets or have any of the elements that we're made of. So when the physicists said decades ago, "Who ordered that?" the neutrino is just one more example of this amazing idea that somehow nature is looking out for us, that the universe is ordered in such a way that we seem to, that seems to be so hospitable to life. The problem, however, is that the best theories of physics that we have are not converging on an answer to the question, how come the universe is built the way that we see it? Why is it so amenable to life? And just very briefly, you know, for example, the leading theory of the world at the microscopic level, that's called superstring theory, that predicts that there are very many ways to build a universe. And this has discouraged the physicists because they wanted unique ideas that would lead to a unique universe. And now they have ideas that are leading to many different possible ways to build a universe. To make matters worse, the other leading theory of physics, which describes the universe at a very large scale, it goes beyond the Big Bang. It's called the inflationary universe theory, and for which there's a lot of evidence now. This physics of the cosmos on a grand scale predicts that there are many universes being built all the time. That is, that our own Big Bang was not unique, that there are other Big Bangs taking place very, very far from where we are now, elsewhere in space, and that those big bangs don't necessarily have to produce universes that are similar to our own. So we have the worst of both possible worlds now. We have one branch of physics telling us that somehow there are many ways, very many ways, to build a universe. Another branch telling us, oh, and there are many universes. And now physicists are wondering, are we starting to look a little bit like biology? Okay? So most of these universes, other universes, would not lead to life, yet our own universe is fine-tuned for life. And so we're in a bit of the same position that biologists have been in. When you ask a biologist, well, why do frogs exist? Well, there's, isn't evolution random? And, it's contingent. And if you ran evolution over again, maybe it wouldn't be the same, and you wouldn't get frogs. And whereas physicists, Einstein said God doesn't play dice with the universe. There's a reason why there are certain laws and why the universe is built the way it is. Ironically, biology has been moving in a different direction in the last 10 or 20 years. We've learned, for example, that that evolution is not quite as random a process as we thought. For example, we have lots of examples now of convergent evolution. I wanted to give you just one example. Mammals all have one thing in common. I don't know if any, and it's not breasts and milk. It's the three tiny, and this astounded me, it's the three tiny bones of the inner ear. It's the one thing that all mammals have in common. And there are different groups of mammals. There's us, the placental mammals, and there are the platypus branch of the family, and then there are these marsupials, koala bear. And it used to be thought that that there was some common ancestor to all branches of the mammal family that that evolved these wonderful bones of the inner ear. And it was recently discovered that's not the case, that the inner ear actually evolved 3 separate times in each of the 3 groups. So it's almost as though nature is sort of pushing us in the right direction. It's not clear what to make of all this, but it's ironic that at the time when biology is moving in this direction of understanding that there are certain underlying simple rules that seem to be pushing evolution in various directions, physics is going in the opposite direction, is now having to worry about multiple universes and the roll of the dice. So just to summarize, physicists are left with this horrible question for the 21st century. Will physics find simple rules that explain why we're here? Or are we, quote unquote, merely the random roll of cosmic dice? Now, I want to just end with, very briefly, on an optimistic note, which is that, well, we know that even infinite complexity can arise from very, very simple rules. And I want to show you one particularly nice example of that has brightened the last century. This is the most intricate pattern in the world, and many of you will have seen this in one guise or another. This is the so-called Mandelbrot set, or Mandelbrot pattern. It's the ultimate peak-by-number image. And I need to appreciate it. I need to just explain how this image is created. You start with a blank canvas, and then you label every point on the canvas with its mathematical coordinates. So, X and Y coordinates, so you were graphing. And so every point has a pair of numbers. And then the mathematicians apply one simple rule to each of those points. They do something to those coordinates, and the rule spits out another number. And that number becomes your paint by number, and then you have to assign a color to that number. So, and then they draw they draw the result of that. Now, because there are an infinite number of points on a canvas, in principle, this is a pattern that is infinitely complex and fine if you could zoom in on finer and finer points. And that's what we're just about to do. So what I'm going to show you is the pattern as seen by an artist who lives in Cambridge, Catherine Maguire. She's actually an artist who didn't normally work in this medium, but she fell in love with the pattern. So I'm just going to start zooming, and you see we start with this wonderful heart shape, and then there seems to be something weird going on along the edges here. where it's yellow. So let's zoom in there, and we're going to take a big zoom in to our first step. And we start to see these amazing patterns. Now, I just remind you that the artist selected the colors, but nature chose the pattern. In other words, the pattern comes from nature and from mathematics, but the particular colors that we see come from the artist's choice. Okay, so let's zoom in on that center part now in that box. Okay. And we're going to zoom in here a little bit further. And you start to see, I don't know if you can see that, this little, you can see almost like that little heart shape reappearing again. Now it's really starting to get, all right. Okay, let's zoom in some more on that. We start to see these fantastic patterns. Now, no human being has ever seen the whole Mandelbrot set, the whole pattern, because it's infinitely complex. And you could zoom in on any spot here. And so there are people all over the world who specialize in different regions of this incredible pattern, and they zoom in on it, and they see things and patterns that nobody else has ever seen. It is literally an infinite universe. And I'll explain that a little more. And now Catherine decided that she wanted to zoom in here in this spiral area, and you get this incredible spiral banister. And she wanted to see, well, what's happening on the handrail here? And again, you start to see spirals within spirals. She's going to zoom in on that. It's another spiral staircase leading us ever inward. At this point, the original image that we saw is we've now expanded so much that it's actually larger than the entire Earth. So we've really zoomed in. Incredibly complex pattern, and yet an incredibly simple rule that gave rise to it. Okay? Let's just keep zooming in. Zoom in some more. Up, and now there's something weird going on here. Let's see what that's all about. Oh, this incredible spiral. Zoom up, and we see our little pattern again, yet again. Zooming in. And one more time, there's another little pattern in here, and it turns out to be yet another little heart shape. And at this point, the artist ran out of computing power. You need a more powerful computer. So you could go on, in principle, you could go on infinitely long. I'm going to end here. I think it's such a fitting and beautiful pattern because it really brings back our original idea of scale and what happens when we look at smaller and smaller scale, and also this idea that there is an underlying simplicity that can lead to amazingly complex things. And this gives us hope that in the 21st century, physicists will discover the very simple rules that lead to an explanation, perhaps, of why we're here. Now, I want to leave you, on the other hand, I want to leave you with two thoughts tonight. One is a wonderful quote from Catherine McGuire. She said, the reason I love these patterns is because, like us, it's finite on the outside, but infinite on the inside. And the final thought I want to leave you with is from the great physicist John Archibald Wheeler, who said, suppose that physicists could come up with the ultimate equations that describe the universe. Really the theory of everything. Suppose they could. And they write them all down on a blackboard. And they're very simple equations, so there aren't a lot of them. But they write them down on a blackboard. Here they are. They explain the entire universe. And then you take a magic wand and you wave it over the equations and you say, fly. But the equations just sit there on the blackboard. So you wave the magic wand again and you say, fly. But they just sit there. But the universe, said Wheeler, the universe flies. Leave you with that thought. Thanks very much. Thank you for coming tonight.
We'd like to take a few questions. We'll have to wait, and you do need to speak into the microphone so that we can hear you. So please, if you have questions, raise your hand or your foot down in front.
Yes.
Why are you focusing on life as opposed to just molecular structure?
Many physicists actually are uncomfortable focusing on life, and so they do use the term structure instead of life. The idea being that if only we could create stars, planets, and galaxies, then we're well on the way towards creating life. I choose the word life because there are many other reasons why I think that our presence in the universe, it just sounds too new age, but so I don't want to do that. But there are many other lessons from physics and biology in the last century that lead me to believe that there is this wonderful dialogue between us and nature. And I think that the fact that we're here, and the fact that, for example, I mean, why does we're carbon-based life? It really is an accident of nature. It seems to be an accident of nature that the carbon atom exists at all. Nobody has really explained that yet. And I think that really cries out for an explanation.
As opposed to other atoms?
They're a miracle, too.
Another question. Up above.
Hi, and thanks for a great lecture. My son here is in fourth grade. He's doing a little paper on black holes and odd behaviors of black holes, and I was learning from his paper that black holes, because they're rotating, the singularity can be like a ring instead of a point. And then this sort of picture book went on to describe sort of this, if you zoom into that, it's not just like a line or something. It can be like, they said, like soap suds or quantum foam. And they had an odd kind of artistic depiction. And I was just wondering, for my sake, but my son's sake here, for his little paper, is that, could that relate to the fractal, the infinite form of the fractal? Is there any kind of correspondence there?
Yes, absolutely. It does relate in the sense that I mentioned that as you get closer and closer to a black hole, your scale actually shrinks, so that in fact there's more and more space as you get towards a black hole. In a sense, a black hole creates some additional space right around it. As you get inside a black hole, now there's a whole controversy about what really happens inside a black hole, and there are lots of people studying it, and I'm not sure I want to go there, except to say there are physicists, practicing physicists, who believe that black holes actually lead out to another universe, that the other side of a black hole is a white hole. Very controversial, and some people say, no, there are theorems that prevent that and so forth. On the other hand, you mentioned spinning black holes, and it was just discovered, I'm not sure I want to go here, but you probably have heard that there may be more than 3 dimensions to space. There may be additional dimensions. And if there are, then a lot of those theorems that apply to black holes turn out not to apply in higher dimensions of space. So, for example, in 5 dimensions, a spinning black hole actually behaves very differently from the way it does here. So nobody really, and no one really knows what happens inside a black hole. We are, of course, the best we can do is to study what happens outside a black hole, and that's why there are so many missions from NASA and other agencies to study what happens right near a black hole. I'm not sure that answers your question.
There's a question up here.
Thank you. Hi, I also have a question regarding black holes. Hypothetically, could you see a black hole from the other side? For instance, if you were to look at a black hole from Earth, if you were to be rotated 180 degrees around the black hole, would you still be able to see it from the backside, so to speak?
Yes. The black hole is really a sphere, and so you can see it from any direction. Or not see it because it's black. The way we see black holes, of course, and because it swallows light, the way we see black holes is that a black hole is so powerful that when matter falls into it, it heats up enormously and becomes so hot that, in fact, it gives off X-rays and other forms of light, and we can see those X-rays. And you can see that from any direction. Yes?
Thank you. Just wondering, when the neutrinos destroyed the star, triggered the explosion, it kind of looked like a black hole.
Oh, here's our 21st century physicist. Good eye. In fact, that's exactly what happens in this particular star. When the star nears the end of its life and collapses like that, the inside of the star forms a black hole. And so you get a remnant, basically you can think of it as almost like the pit of a peach or something. The black hole forms at the center, and then the outer layers are blown apart, and that's what goes out into space.
Oh, thank you.
So there is a black hole in it.
The question in the center, young person up here.
Is that over? My question is why doesn't the supernova blow out in all directions?
Oh, another incredible question here. Nobody's quite sure, but it probably has to do with the fact that the star is spinning. And when the star spins, it has a north pole and a south pole the same way that the Earth does. And so when it explodes, it may direct material to the poles. So they go out in these beams. But in many supernovae, it does go out in many different directions. It's not just in those two narrow directions that you saw in that animation. And in fact, people are studying this actively now.
We'll wrap it up. One more question up here in the center.
Hello. You mentioned about how the ruler or the measure of distance in space would have shrunk. Would a minute now have been the same as a minute at the Big Bang?
That's a great question. The ruler is shrinking with time, but time itself doesn't change. So time, no, it doesn't. It's an interesting question. Time does change in these other places. When you're near a black hole, it slows down. Closer to the surface of the Earth, it slows down. But in the universe as a whole, there is something called cosmic time. As the universe expands, that time basically ticks at the same rate. So if you were back at the black hole, your watch would run normally, but you wouldn't have any room to move around because the universe, space would have been so much smaller, at least the part that we see now.
Roy, thank you.
Thanks so much for being here.